is considered to be generally binary, right? And then we have this spaghetti Turing machine that just does these transitions, right? And in the end, you get some output, right? And that's great, but what does it mean, right? And I personally like to say we have different levels of understanding things, right? And I want to move up to higher levels of understanding, all right? So I'm going to be talking about, in fact, I think I just designed these slides at the end of last time I taught it. So these ideas of level of abstraction kind of got done last time. So anyway, I'm going to try to impose on this thing meaning to the input, meaning to the output, and structure to the code. All right? So the input, it's binary, but it could be representing this face, right? And then the output, it's binary, but it could be representing the same face where we did a little, not PowerPoint, what do they do? Photoshopping to make it look nicer, right? If you think you don't look as nice as the people on TV, it's because they're lying, right? We removed the wrinkles, right? So what is right, we're adding meaning here, right? Meaning that's not really there. Everybody follow me? Right? And another thing I'm going to impose on you, remember I told you that we could teach that you name the states Q1, Q2, Q3, but I'm going to require that you give names to your states, right? This is higher meaning that has nothing to do with the Turing machine, right? It's just so that somebody reading your Turing machine can understand it. So we're going to add new meaning, right? And what is the meaning going to be? This is just a string, which is the name of the state, right? And I'm going to add meaning to it to mean it means I'm on line 39 of my code, whatever that means, because we don't have code, right? Turing machines don't have code. They just have states and transitions, right? But I'm imposing extra meaning, and the extra meaning is that we're going to be compiling from something that looks more like Java. And when our Turing machine's in this state, our Java program is going to be on line 39. Right? Does that make sense? And when I'm in this state, my Java program is going to have a bunch of variables. Now, again, Turing machines don't have variables. Right? So a question I could well ask you is, hey, does your Turing machine have a value x, and does the value of x of your Turing machine have value 3? And what should you answer? No! My Turing machine doesn't have variables. It doesn't have values. It's only in a state, and the state means nothing. Right? It's this higher level that we're adding. We're adding meaning to this. Right? This is saying, my Java program that's out there in my imagination has a variable x, and the value of variable x is 3. Right? Are people understanding this? Right? How we're adding meta knowledge. It's kind of like, similarly, your brain. Right? What does your brain do? It has a bunch of neurons and they fire. Right? But somehow, out of your mouth comes poetry of love to your girlfriend. Where does that meaning come from? Right? It's some weird higher level of abstraction than the Turing machine itself. Right? Does that make sense? Right? So we're going to add structure. We're going to stop allowing, I'm going to impose rules on you. Right? Really, a Turing machine can have go-tos, right? You can jump to any state you want, right? But I'm going to impose on you rules, right? I'm going to make you clean your room. And the rules are going to be Java. We're going to add Java-like structure to your Turing machine, right? And so in some ways, not only are we going to prove that Turing machines can compute anything, we're going to say even if you impose these rules, they still can compute anything. So why have a weird Turing machine? Because it's only going to confuse people. Right? Everybody good? All right, so in our loop invariant, we're going to impose loop invariants. And, right? And instead of designing our new Turing machine, we're going to compile. Everybody good? I said all those things. And so this is just a quote from Donald Knuth, which I used various times, but I don't think I've given it to you yet. It says there are different levels of abstraction, right? This is an abstraction. This is abstraction. And you want to be able to do well in the world, you need to move between them, right? You can think about your computer as AND gates and OR gates, but then you can move up various levels of abstraction to think about it as a machine that can drive, right? And in fact, when I was in Africa, I made a set of slides that does that. We start at the bottom of sand, and we build ourselves up levels of abstraction, saying, how are we thinking about this level until we get to machine learning? So those slides are there if you want to see them. Right? So, and we want to be able to understand complex things in simple ways. All right, so how much time do we got? Feels like we're running out. 9 minutes. All right. So, we're going to go through various levels of abstractions, and when I made these slides, I numbered them 0, 1, 2, 3, 4. I forget now how many levels of abstraction there are, and the numbers don't mean anything. I made this up when I made these slides, right? You're never going to see these anywhere else, right? So the bottom level of abstraction is, what do I have? I have a Turing machine, right? It has states. It has a delta function. It has tape, 0 and 1, right? That's all we got, right? Everybody good? And then, right, what is this level of abstraction, right? The input's a 0, 1 string. We have a finite set of states that we can number 1, 2, 3, right? The actions are defined by this transition function, right? Now we come up to level 1 of abstraction, right? We're gonna give names. All we're doing is we're renaming the states, right? So we're really doing anything? No, it's the same Turing machine. We're just renaming the states, all right? So we can interpret this string to be a face, right? We can give meaningful names to the states, right? As I've done before, meaningful names, right? And what does this give to us? By just naming the states, it gives us new ways of thinking about Turing machines, right? I can now talk about the Turing machine knowing the value of x, right? Right? I can imagine it has a line of code, right? I can imagine it's remembering the value of x and y, right? I can imagine that it can execute things like this. This is the kind of, so when I say you have to write a Turing machine, right, this is the kind of thing I want you to say, right? I want you to say, I'm in line 39. If I have these values, right, and I read a 1, then I go to line 40, and now I'm going to have these values, right? Again, this is just a delta function, right? So I haven't done anything except rename states, right? Is everybody good? All right, so now we're going to have meta names and meta transition function, right? Before we had each state was given a name, right? Now we're going to have meta names. We're going to have a pattern of naming, and before we had entries of our data function, of our delta function, now we're going to talk about whole blocks of the transition function, right? So what do I mean by that? Well, how do I talk about a block of states? I can say, hey, now there's no state whose name has x equals x prime in it, right? That's not a state, right? It's a meta statement. It's a meta statement meaning for any value x prime in that range, and any y prime in that range, we're going to have a state by that name, right? Does that make sense? How many states do I have? 5 times 5 is 25. Right? Everybody got, I'm talking about 25 states with 25 different names. Right? But the advantage of this is I can talk about them, right, in a meta kind of way. Everybody getting this? And then, now I'm going to talk about a transition function. And instead of filling out the whole table, right, I could make you fill this whole transition table out. It's a big table, right? If you want your Turing machine to do something great, it might have a billion states, right? That's a big table. Right? So we're going to talk about filling in blocks of the table. This is going to say, right, if I'm in a state for an arbitrary x prime and an arbitrary y prime, and C is an arbitrary thing from 0 to 1, then if I'm in this kind of state, then I'm going to go over to this kind of state, where I'm in line 40, the value of x hasn't changed, the value of y has changed to whatever was here, right? And I write the C back, and I move my head right. Right? Now, have we changed the power of Turing machines? Right now, the Turing machine, what is it doing? It feels like it's reading the value of C off the tape and storing it in Y. Right? That's what it feels like it's doing. Is it really doing that? No, it's still just the table. It's still just states, right? So now we can come up to another level of abstraction. Now I can say, hey, that block of state transitions, what's happening? Well, what's actually happening at line 39, right? I'm making y, whatever value stored where the head is, I'm reading it in and I'm putting it in y, right? And I move my head right. That's what that line of code was doing, right? Now, when I said I was going to get you to compile Java code in the machine code, I was kind of lying to you, right? The code we're going to be is going to look like this, right? It's a little more Java-like than Turing machine. And you're going to see code that looks like this, and you're going to compile it into a machine code, right? And come on, guys, you just saw it. It wasn't very hard, right? All that's required is for you to understand it, and you can do it, right? But half of you will give me garbage, right? And I'm going to look for anything that's not perfect, because it's going to convince me you don't understand what's going on. All right, so people are hustling. Are we done? I think we're done. We have more levels of abstraction that we'll do later. All right, have a good, today's Tuesday, so I'll see you on Thursday. We're going to start by defining at the very bottom, your brain has neurons, and they fire. Right? Bottom level of abstraction. What is a Turing machine? All right? A Turing machine has a finite set of states. Right? Every Turing machine. When I build a Turing machine, what do? I tell you how many states I have. I give them names. Well, I could call them Q1, Q2, Q3. Right? And then I tell you, and then you have this infinite tape, right? I tell you, what are you allowed to store in a cell of your tape, right? What's my alphabet? Is it 0, 1 blank? Am I allowed ASCII? Am I allowed digits? Right? But it's finite, right? You could also tell me what the alphabet is for my input, but chances are they'll be the same, right? Could be different, right? And then I'm going to build a table. Remember I said it's all about table lookup, right? So the input, if we're doing binary, then the input's going to be a binary string. We're going to have a finite set of states. Here I have 2,500 states. right? Do you want to be getting down and personal with each one of them? No, right? It's a lot of states, right? And then I define actions. I find a table, and the table is called delta, right? And what does the delta do? It tells me the Turing machine, in this case, is in state 2. What state am I in? And the head, right? The head's going back and forth in the tape, and we keep changing the contents of the tape. We don't know where the head is. We don't know what the tape contains anymore, right? It contains something. And what is the character? We can look at what is the character where the head is on the tape. And it's a 1 in this case, right? So then the function delta tells me what state should I be in next? What character should I write onto the tape, because I'm allowed to change it? And do I move my head right or left? Or if you're lazy, do you leave it stationary? Right? Everybody get that? That's what a Turing machine is. Right? It doesn't have variables x's and y's. It doesn't have lines of code. It doesn't have meaning. Right? Everybody got this? You start off with the input on the tape. You run these rules. Hopefully it stops at some point. Why? Because one of the states is a halt state. Right? Goes into the halt state, it halts. And then whatever is on the tape is called the output. Right?
Is that why the halting problem is uncomputable? Because if you were to represent it with a Turing machine, you'd never be able to draw the halt state in some cases?
No, we're going to prove that the halting problem is undecidable. All we're going to use in the proof is that an algorithm, every algorithm, has a finite description. We're not going to talk about halt states. All right? But any good model of computation is going to have a way to stop. Right? Because if it doesn't stop, it's not very useful to us. Right? In this case, it stops by it transitions into a special state, which is called the halt state. Right? Everybody good? All right. So now we could say we've learned about Turing machines. We could get you to write a few of them, and it would be hard, right? And that was what we would do. But that's not what we're doing here, right? We're trying to have levels of abstraction, because that's how you gain deep understanding of things, is by looking at the same thing at higher and higher levels of abstraction, right? In fact, to me, what we're doing here is we're moving away from this is a theoretical useless course to how is this actually practical to me, right? What's actually practical is can you think at different levels of abstraction, all right? So we're going to add some abstraction. And I think what I want you to do is we add them. I want you to observe two things. The one thing that we're observing is just how much more understandable it is, how much more intuitive it is to a human thinking about it, right? That's the one thing I want you to understand. And the other thing I want you to understand is in reality, nothing is changing, right? In reality, the Turing machine is still just the Turing machine, right? It's a bunch of states and state transitions, right? All we're doing is we're looking at it from slightly different views, all right? We're giving names to things. We're laying meaning on top of what's there, all right? Can everybody, that's our goal, right? Everybody got our goal? See how it doesn't change, but how it's prettier, right? And to be able to understand it at all the levels, right? So does everybody understand this bottom level, right? It's pretty straightforward. All right, so now we're going to go up a level, and all we're going to change is we're going to give new names to the states, all right? We're not going to have X variables or Y variables or lines of code. We're not. We're just changing the names of the states. All right? And here, well, it's not changing the name of state, but, we're giving meaning to this string of zeros and ones, right? We're now thinking it's not a string of zeros and ones, it's George Clooney, right? And he has wrinkles, right? Everybody got what we're adding meaning to it. And then we're adding meaning to the states, names, right? So here we're going to have a new name. It's a string, right? What's the name of a state? Is you attach to every state a string to say, hey, this state is called 385, or this string is called Bob, right? Right? A rose by any other name is still smells so sweet, right? So, right. But now, how does this change anything? Have we changed anything in the Turing machine? No. But how does it give us meaning? Well, we can now imagine that there's this thing called code, and we're on line 39 of it, right? We can imagine that the Turing machine is remembering the value of x and y, and currently x is 3 and y is 0. Right? We're imagining that. But it's all in our imagination. Right? Everybody good? Right? And then, we just look again. We're just writing down the delta function again. Right? Delta function says if I'm in a state with this name, and I read a 1, then I'm going to go into this state. Right? And still, do we have meaning? Why are we going into this state? Why do we go from this state to this state? I don't yet quite have meaning to why I'm doing that. Right? Everybody good? Now we're going to go up a level again. We're going to talk about metanames. All right? So this is a way of talking about a set of states all at once. The Turing machine, remember it had, that one we gave had 2,700 states, and I don't want to talk about each of them, right, separately. I want to talk about them kind of friends, all my friends and relations. I want to do these things to them, right? So here, I'm now going to say, well, let x prime be a number between 0 and 4, and y prime be a number between 0 and 4. And then I can talk about, this state here. Now, there's no state that's going to have that name, right? The states are going to be called x equals 3, y equals 4. That's the names of the states. But here's a way of me talking about them sort of collectively. Right? Everybody see that this is a metaname of a state. Right? People with me here? Everybody following? All right. So, and what does that allow me to do? That allows me to fill in an entire block of the delta function in one foul swoop. Right? I'm going to say, for every x prime and y prime and c in that range, if I'm in this state and I see a c, then I'll go over to this state. Right? And I just filled in 5 times 5 times 2. I just filled in 50 lines of the table. Yep. I don't know yet. Right? I don't know. It's a good question. Right? Do we have meaning yet? Do I know why I'm doing this? Right? We started off with the Turing machine, which is making all these arbitrary transition moves. And do I know why it's doing it? No, not really. I mean, you have to be really into the nuance of why it's doing it to design this thing. Now you're asking, why am I doing this? Well, do we have meaning there yet? Right? We're going to get meaning in our next level. Right? Everybody good here? Yeah?
So the number of states depends on how many lines we have, or
we're going to count states. Right now we're doing the levels fast. And after we do the levels fast, we're going to redo them slowly. And when we redo them slowly, we'll do things like counting states. All right? The first state? There will be some state called the start state. And we'll have to bring that into it as well. Right? Everybody good? Right? So now, let's go up another level. What do you think our next level is going to be? We need to answer her question. Right? We're trying to get some higher meaning. Why are we doing this? Right? Why we're doing it in some sort of more human sort of way, some sort of more computer science sort of way, what's happening? Right? So now we're going up to, it's not going to be Java code. I say that because you guys learned Java. Right? It's going to be pseudo-y code. Right? We're going to say, hey, look at, I was in line 39, I went over to line 40, right? And all of these, everything I said here, I went from line 39 to line 40, right? So what's happening in line 39? Well, I'm taking the value that's in the tape, and I'm reading it into my machine, and I'm storing it in my value y, right? There's meaning. Right? Nothing has changed in the Turing machine except we're adding meaning on top. Right? We're saying, and we're, in some ways, what's changing in the Turing machine at the bottom is we're restricting it to say you can't do anything you want. And you have to have these nice patterns so that we can line meaning on top. Right? If the delta function was random looking, I couldn't be adding meaning on top. Right? Everybody good here? And, right? So this is what I'm saying. We no longer allowing spaghetti code, right? Now we need loops, so we need function calls. We need things that look like Java, right? So, and now we're going to have another level of abstraction, right? This level of abstraction was of lines of code, actions, right? And if you were at the tutorial on Monday, we went over again loop invariants and how we're going to have a loop invariant that we're maintaining, right? So that's another level of abstraction, right? I'm saying, what's my loop invariant? What am I going to maintain, right? At the top of my loop, I'm going to have a loop, and at the top of the loop, I'm going to say what is true, what's the picture that's true, what's the relationship between my variables, right? And we're going to talk about how do you establish the loop invariant, how do you maintain the loop invariant. This is, if I'm at the top of the loop and the loop invariant's true, and I haven't exited, and then I execute the code in the loop, then when I get back to the top, the loop invariant, the picture, the relationship between my variables will be true again. Right? Everybody following that? We're adding more and more layers. And what I just did in 3101, just before running over here, was saying, suppose all you know, in fact, I'll tell you what's going to be on their test. I'm going to give them a precondition, a postcondition, and if I'm nice, I'll give them a loop invariant. Right? And they need to develop code and prove that they maintain it. So we're going over and over. How do you get code from a loop invariant? Right? And so that's what we're going to do, is we're going to say, well, we start with our loop invariant. At the highest level of abstraction, I'm going to come up with a loop invariant. And then when you take 3101, we're going to talk about how to compile that down one level of abstraction. So now I have code in the loop, right? And then how do I compile that back down a level? So I have, I need states. I need to build the Turing machine, right? I need to say what are the names of my states and what are the transition functions of my Turing machine, right? And if we went all the way down, right, there's some, if we wanted to feed it to Turing machine into Wolfram Alpha, probably it would require me to name the states Q1, Q2, Q3. So then I'd go down another level of abstraction, right? So now we're running an actual Turing machine, right? Does that make sense? And once you have this ways of coming down, we could just as well start with the same loop invariant, but as we come down, we're going to build Java code, and then we're going to compile it into machine code, and then we're going to run it machine code on your computer, right? So there's ways of looking at it. It doesn't matter whether my bottom computer is a Turing machine or whether it's an Intel chip, right? Everybody seeing this? So, all right. Everybody good? So I think we're going to now do it again, right? These were our levels of abstraction, and let's go through each one again and make sure that we understand it. All right? So I'm a fan of Winnie the Pooh, if you haven't noticed from my sweatshirt, right? You should all read the original and the Tao of Pooh. And anyway, he's a very, very little brain if you don't know who he is, right? And so he can't think very hard. He can just follow simple instructions. And he has a little blackboard on which you can write things, right? And so there he is. And right now he's living inside of a submarine. Why? Because submarines have little periscopes up, and they can see just what's in front of them, right? And so he can just see his the current value of where the head is on the tape. And what is this control, right? It's not that, so we were having an argument with someone last class, is the tape controlling? No, it's this finite state automata, the states, that is controlling things. The delta function is controlling things. And how can you understand it? Well, you can understand it by a little piece of Java code, right? That's what we're translating it into, a little piece of Java code. And what does this Java code have? Well, at compile time, it has a finite length of code, right? And at any point in time, it has a current line of code, right? And what else does it have? There's a finite number of variables, right? And can it remember an integer? No, it can't remember an integer. Integers are big. Every variable has a finite range, right? It can remember a bounded variable, a bounded integer, right? And so that is, that's all this has to do with the delta function, right? That's the state I'm in. And then what do I also get to see? I have my little periscope, and I can see one character from the tape, right? Everybody got that? And there. And also, you can see how I'm doing it? That was pretty exciting, right? Everybody saw it move? Oh, there it goes. It moved, right? So I'm also, Pooh Bear can move the periscope left and right. Everybody got this? All right, so now I talk about Pooh Bear. So I'm going to forget about the submarine mostly and focus on what Pooh Bear knows, right? So he has a blackboard or a whiteboard of a fixed size that he can write, and on that board he can write anything he wants. All right? So let's not limit him. Let's just say he's limited in the size of the blackboard, right? And on that blackboard, maybe he's limited in the size of his font, right? Because we don't want to be doing little things, right? He only can write ASCII characters of a certain 11-point size, right? But he can write whatever ASCII characters he wants on it, right? So somebody asked about how many states are there, right? So let's do some state counting and pay attention, because on pretty much every test I've ever had, I've made people count states, right? I'm going to make, in fact, a good way to test to see whether you're understanding what's going on is, right, I'll give you some Java-like code. I ask you to compile it into a Turing machine. And then I ask you, how many states do you have, right? And it's not just a matter of can you count them. It's a matter of do you understand what's going on here at all? Because if you don't understand what's going on, a good way for me to find out is you give me the wrong number of states, right? So I'm going to somewhat put more emphasis on the number of states than you think I might should, because it shows me that you're understanding. All right? So let's count the number of states, yeah? Do I have 2 thens? All right, thanks. My secretary is somewhere here. He will remember that. All right, so that's you. All right, 2 thens. Thank you. All right, so now suppose on my blackboard I can store 4 bits, right? How many different things could be written on there? Right? I could store 0000, right? Or 0001, right? How many different things could I store there? 16, right? So if what I'm writing on is I'm writing on bits, and I can write R of them in the size of my paper, then the number of different states is 2 to the R. Right? Everybody following that? Because the state that I'm in is determined by what's written on the blackboard. Right? And the number of states I have is how many different things could be written on the blackboard. And if what I'm writing on the blackboard is R bits, then there are 2 to the R different things that could be on the blackboard, and I have 2 to the R different states. Right? And what am I going to call the states? If this is written on the blackboard, what should I call the state? Right? That's a perfectly good thing to call the state. Right? Everybody got that? Maybe we could say whose blackboard equals. Right? Everybody good? People following this? Yep. Yeah. Yeah. If it was R hexadecimal, then it would be 16. If it was R ASCII, it would be 256 raised to the R. Right? So let's do another one here. Suppose I have 100 lines of code, and X has one of 5 values, and Y has one of 5 values. Then how many different states are there? A 100 times 5 is 2,500, right? 2,500, right? Which I think is the number I had on the slide way before. Right? Everybody see that? Right? If this is what's written on the blackboard, how many what's written on the blackboard? Is Pooh Bear has to remember which line of code he's on. Pooh Bear has to remember the value of X. Pooh Bear remembers the value of Y. So that's what's written on his blackboard. Right? So, and what do we give? How do we name the states? We give them meaningful names. Right? Everybody following this? So if these are the names of my states, I say, how many states do I have? Well, there are 100 values for this. There are 5 values for this. There are 5 values for this. This is how many states I have. Right? Everybody see that? And you can see how, well, the math is a little tricky, and if you do the math a little wrong, I don't care. Right? Maybe if you did additions there, I might get upset, but if you forgot the halting state, maybe these are your states and the halting state, and so the answer is 2,501. You know I don't care. Right? It's like, but do you get the big picture here? Right? Everybody good? Yeah? All right, so I'm trying to give you this intuition that Pooh Bear can write whatever he wants to write. Pooh Bear can decide that he wants to have code that has 100 lines, and that he wants to store the value of x and the value of y, and they have to be within these ranges, right? So what I'm writing here is what Pooh Bear would write on his board. Pooh Bear has written line equals, this is what he has written on his board. So that's what I'm going to name the state. And it's what, when I'm in the state, what do I want to name the state? It's when I'm in that state, what do I want to know? Right? If I was in a different state, right? If I was in the state where this was a 3, then I would know something different. I would know that y was 3. But I'm in this state. And in this state, y is 2. Right? Everybody getting this? Yeah? Nothing. Yeah. Yeah, we're not talking about tape right now. Remember, at the bottom level of a Turing machine, it has states, has a certain number of states. And all we're doing is we're moving up and we're giving the states names, and we're deciding how many states we want to have. All right? So instead of saying I'm going to have state Q1, Q2, Q3, I'm going to name them this. And then how many states do I need? Because if you're building a Turing machine, you need to know how many states I need. Right? This calculates how many I need. That's all we've done so far. Yep? Well, it's choosing, right? Let's look at a tree here. I have 100 choices for line number, right? And for each line number, I have 5 choices for x. And then for each of those, I have 5 choices for y. Right? So now how many leaves do I have? Right? A path would tell me a value. I choose a value for L. I choose a value for x. I choose a value for y. That gives me one state. Right? How many do I have? 100 times 5 times 5. Yeah, you did this in some course, didn't you? I mean, it's not permutations. I mean, let's do another example here. Suppose x3 is in 0 to 9, and x2 is, and x1 is, and x0 is. Right? Then I want to know what is a state? Well, x3 equals 8, and x2 equals 5. Right? Or I could write it down 8, 5, 2, 1. Right? This is the value. So I got 1, 2, 3, 4. Right? This is the value of x3. This is the value of x2, value of x1, value of x0. Right? How many of these are there? Well, the biggest one is 999. The smallest one is 000. Right? The number of them is 10 times 10 times 10 times 10. What's your biggest one? This, right? 10 to the 4. Right? Is that making sense? Everybody see these ways of counting? All right. So that's what he's written on the blackboard. Right? Just like I promised. All right. So now let's go back to our lowest level of a Turing machine. Right? What is a Turing machine? It has the states. It has what might be seen on the tape. Right? It says I'm in state 2. I'm looking at the character 1. What do? I look up in the table. The next state I'm going to go into is state 447. I'm going to write a 1. I'm going to move my head right. Everybody see this is what a Turing machine is. Right? And so now we're going to add on, oops, aren't we? Here we're going to add on meaningful names. Right? So all we're going to do is rename the states. Right? So that state, Q2, is no longer called Q2. It's going to be called that. Right? And state 447 is going to be called that. And so then we just write those names in there, right? And our delta function comes this, right? Nothing happened except I renamed the states. Everybody following that? All right? That was the name of the state you're currently in, right? That's the name of the character that you're looking at. That's the name of the next state. That's the value you write. That's whether you move the head right or left. Everybody getting this? I just remind you periodically because my guess is you haven't actually memorized it. Right? All right, so now we're going to talk about metanames. What does it do? Well, let's consider, we're going to take a block of this table and we're going to fill it in all at once. All right? What we're going to say is in this block of the code, we're going to have states of the form, I'm in line 39, right? And everything in this block, I'm going to be in line 39. And I'm going to have all the various values of x, all the various values of y, right? So how many states are we covering here? 5 times 5 is 25, right? That's 25 states, right? Right? It's 25 states. And then I'm going to say C is either 0 or 1, right? Because if C is a blank, I'm going to do something different, right? I'm going to fill in this part of the table separately, right? But if what I'm reading is a 0 or 1, then, right, for all of those various values, I'm going to say, in one foul swoop, I'm going to write this down, right? Is this some sort of magic code? No. It's a meta way of filling in a block of the table. Right? Everybody getting that? No. What aren't you getting? Well, did you get how this way we have states of the form, they're all line 39, there are 5 values here, 5 values here, we've got 25 of these, right? So I'm saying for every, right, and then we got 2 values here, right? So for all our values within our particular range, right, here I try to get things on the slide. Really, C is 0, 1, right? So for all of these values, if I'm in a state that looks like this pattern, and I read a character that has that pattern, then I'm going to go into a state that has this pattern, and I'm going to write that pattern on the tape, and I'm going to move right.
So do you write like line 40 and line 39?
No. See, you're thinking about it as code, and I'm thinking about how do I fill in this table, right? I want to know, right, here's a big block, this big purple, pink block, right? I want it in one step how to fill it in, right? For each square, I could write it in myself.
I understand that, but I'm saying like, so right now we're at currently Q2, but then in the command line where it says like Q line equals 39, like where I'm looking at Q2,
Yeah.
and then
Yeah.
so
So Q2 is no longer called Q2. Q2 is now called line equals 39, x equals 3, y equals 0. Right? So since all we did was change the name, can you buy that if I'm in a state with this name, and I read a 1, I'm in a state with this name, and let's do it again here. We go back. Right? I'm in this state. I read a 1. I go into that state. Right? That's how I fill in that little square. right? Now, right here, there's 50 squares. On the test, do you want to fill them all in? No. So I'm going to tell you shorthand to fill them all in quickly. All right? There's a pattern here, right? I'm in a true Turing machine. For every state and for every character you're reading, you can put whatever you want here, right? There can be complete spaghetti go chaos here, right? And I'm saying let's not do that because I won't understand it. You don't want to write it, and I don't want to mark it, right? Is that agreed? Right. So I only want to mark things that have meaning that I can understand, right? I don't want to be parsing your Turing machine, right? And you don't want to be filling it in. So we're going to try to fill this. We're not doing any actions. We're not doing anything other than I'm telling you how to fill in this table. All right? So this equals doesn't mean we're assigning 40 to 39. It's not an assignment. It's how am I going to fill in this table, right? And there's going to be a pattern, right? First off, we want to know what's the pattern of the names, right? And the patterns of the names is every name in this little block is going to be called Q line equals 39, right? And then it's going to have X equals something. Well, which somethings are we going to allow? We're going to allow X equals either 0, 1, 2, 3, or 4. Right? And then we're going to call Y equals something. And what's that something? It's going to be 0, 1, 2, 3, or 4. So how many different states are there? There's 25. Right? And then at the top, C is going to be either this or this. Right? So now I'm going to tell you the metacode. Right? I'm going to tell you if you're ever in one of these states, then the pattern is going to look like this. Right? Where X prime is one of these and Y prime is one of these. And if you have this pattern, right, and C is one of those, right, if C is blank, we're not doing that right now. If C is one of those, then the pattern is what you do next is you leave the name, and then we're not doing actions. We're just names, right? If we were in a state where X was, the code was X equals X prime, then we're going to, the new state will also say X equals X prime, right? If this was X equals 3, this will be X equals 3. If this is X equals 4, this will be X equals 4. We're just filling in this table, right? But here, Y is going to change, right? Whenever, it doesn't matter which Y name we had before, our new name in this whole column will all be Y equals 0. And in this whole column, the name will be Y equals 1. Right? Are you following that? You see how we're filling this table in? Yeah. Well, we're going to do that in a minute. Right? Everybody getting this? I want to be able to fill this table in fast. In order to fill it in fast and for me to understand it, it needs a pattern. Right? And this is a pattern. Right? And when I'm marking your test and I tell the TA to mark it, when they mark this, right, the goal of them is to see, one, is it right? Is it the right pattern? But two, are they getting that we're just doing patterns in the table? Right? If you do anything to convince me that you're not understanding this, then you'll get a 0. Right? Because you need to understand that what we're doing here is filling out a block of the table. Right? Right? Yeah.
Did you, in this step, did you change the range of C or range of Y? Before the range is from 0 to 4, after that is to 0 or 1.
Yeah, but it's a sub-range. Right? And maybe maybe you're right. Maybe whenever you're in line 30, how many states do I need? Right? If I was really counting states properly, I would observe that when I'm in line 39, I have 5 different values of y. But look at when it's line 40, I only have 2 values of y. Right? So when we were doing this thing here, in this line, there's 5 values of y, but in this line, there's only 2 values of y. Right? We could get anal like that. And my request is we don't get too anal because you don't want to calculate it and I don't want to mark it. Right? So what we're doing here is there are states. I'm defining states of the machine that the machine will never be able to get to. Right? The state, line 40 and y equaling 4, is a state that I'm never going to get to. Yeah. Their loss.
So in that case, did you change the number of the states? Does you use number 9 times number x and number y?
If you want to be anal and calculate exactly the number of states that are ever going to be used, then you will not finish the test and I will not want to mark it. Right? Can you see what I'm saying? And if we just say, hey, this is how many states we have, you will be happy, I'll be happy. Right? Does that make sense? Yeah?
So you have the delta and then the Q line 39.
Mm-hmm.
That's the transition function where we're looking at the line plus C and we're going to that state, right? Which is not important.
We're still, all we're doing is defining this table. Right? In fact, let me tell you one way that you can get a 0 really fast. Right? If your goal is to get a 0, right, the first thing the marker should do is ignore names of states and see, do we have delta is our transition function. It takes the state as input. It takes the next character as input. It outputs a state. It outputs a character. It outputs a direction. Right? When I'm marking, that's the first thing I'm going to look for. Do you do that? And if you do not do that, I do not read anything else. You get a 0.
That was my question. Are we doing another transition function on where it goes?
I'm just filling this table out. Right? In order to design the Turing machine, you have to fill this entire table out. And we haven't filled the entire table out. We just filled out the pink box. Right? Now what you're probably saying is, well, where do you go from here? Well, this state is down here somewhere. And we'll have to fill out that part of the table. Right? And we'll do that in a meta block sort of way too. Right? But we're not done yet. Right? In fact, all I've done now is, have I defined all of line 39? Not completely. I also have to know what would happen if this was a blank. Right? If this was a blank, what would I do? Right? I know these are all my states. So for all the 39 states, I know what I'm going to do if C is a 0, 1. I have to say what C will do if C is a blank. Right? We don't do everything in one step, but you know it's a lot faster than we were doing before. Right? Everybody good? Yeah?
It's possible you have the same Q2 that different state at the same time, and do you consider them as different states?
Which? Q2?
I mean the Q line 39 and different states. Since they have 0 and 1, right?
Here?
Yes. How about you have state Q2 and state 1 and state 0 then at the same time?
I didn't understand your question, but let me give an answer and see if they line up, right? This isn't the name of a state. It's a meta thing, right? And we're gonna plug in various things. And if you plug in 3, 0, that would be one state. If you plug in 3, 4, that would be a different state.
I mean, you have thing Q2.
Q2 up here.
Yeah.
Well, this is crossed off. We're not calling states that anymore. Those are gone, right? See up there. We got rid of that and we called it something else.
If state is different, do you calculate them as different states?
If they're different states. I don't. What different? If they're different states, they're different states.
If you have, let's say, Q line 39 and X, right?
Right.
Saying, like, if you have C being either 0 or 1, is that considered
Oh, this? No. No. Let's again review what a Turing machine is. Along here we got states. Along here we have what character is being read. What does delta say? Tells me what is my state, what is my character read, right? So when we're counting states, it's how many states are there. We're not counting the area of the table. We're counting the number of states, right? So here are all the possibilities for this. And here are all the possibilities for that. Does that answer your question? Excellent. Thank you. It's always good to help me understand. Yes?
So, the block you were saying, you were talking about, you were trying to fill, all these Qs, like let's say you had the 50, like Q,
Yeah.
Q50,
Yeah.
are they called Q line 39, X?
They're all, everything there. In fact, I think I got a next slide. Let's go to the next slide. Right? Do I? Maybe I didn't. All of the guys here, right, they're all 39.
Okay. And then, so now, in these blocks, let's say C, which is 0 or 1, do I, like, whenever you have something written in 1 or 0, is that what C means?
Yeah, so
Because, like, some blocks are going to be empty, some blocks are going to be filled, or am I understanding this wrong?
no, we need to fill this whole table in.
Okay.
So if I'm in, what's this table? It says if I'm in this state and I'm reading this character, what do I do? If I'm in this state and I read this character, what do I do? All right? So now I'm going to try to fill in this whole block. Right? What are the states of this block? They're all states of the form. I'm in line 39. X has some value between 0 and 4. Y has some value 0 and 4. So that's 5 times 5. There are 25 lines here. Right? That's how many states are here. And then how many values of C are we considering? 2. 0 and 1. Right? So now there are 2 values of C. Right? So we're going to fill in a table 25 by 2. Right? Even though it looks like it's the other direction. Right? And it's going to all have this pattern. Right? All the way down this guy, Y is going to be becoming 0. All along this column, Y is going to be becoming 1. Right? And the woman who's about to ask us, she still doesn't see a pattern, what this means higher up. Right? All I'm telling you is this is how I'm filling out the table. Right? Later on, we're going to go to a higher level of abstraction and see what this pattern means. Yeah? Why? Because I told you. So what do you actually do on a test? Right? We're never going to write this table. Right? This table is too big and too ugly. Do you want to fill this table out? No. What you do, this is what you write on a test. Right? You have to know what I'm doing is I'm filling in the table. Right? What you're doing is filling in the table. So what you're doing is they're telling me for every state and for every character that I'm reading, right? For every state and every character I'm reading, what my new state is, what character I'll write, and what direction I head. You have to tell me what to put in your table, right? And how do you tell me? Well, do you fill out this whole table? No. You say, whenever the state has this pattern, that's what I'm going to do, right? So this is what you're going to, in fact, the test is all right here, because we got this here, right? This, in fact, this is what the test is going to say. I'm going to give you this, right? What does this say? It says, I'm in line 39. What you're going to do is you're going to remember the value of x, and the value of y is going to be whatever you're reading at the head, and you move the right head right, right? That's the command, the Java-like command that I'm going to give you, right? Everybody kind of follow that as a Java line? If you're in line 39, reading the value of y, and what do I write? I read in the C, and I don't want to change it, so I write it back again, right? Here, right? I didn't tell you. All right, so I give you this. It says read in the value of C and go right. So now you have to translate it into a Turing machine, right? So what you have to say is, well, what names do I want to give my states, right? I know that x is in the range 0 to 5 and y is 0 to 5, and I know that I'm in line 39. So I'm going to have, for every value of x prime and y prime in C, of x prime and y prime, forget C, I'm going to have a state like this, right? I'm naming my states. And then you're going to say, well, I'm in this state. I read some character C. Well, what state do I want to be in next? Well, what line should it be? If I'm in line 39, what line will I be in next? I'll be in line 40, right? And then you say, okay, what will be my new value of x? Because that's what I'm calling my states, right? It's not what I don't have an x variable, right? I'm just naming my states. What will the name of my new state be? Well, the name of my new state will have the same value of x as I had before. Why? Because I don't want to change the value of x, even though I don't have a value of x. Right? Are people following this? It's very abstract. Right? And then I say, in my name of my state, what do I want the name of my y to be? Well, it's going to be whatever I've read. In this column, it's going to be 0. In this column, it's going to be 1. Right? Okay, that's my state. Right? Now I have to think, I have to remember to write a value into the cell. What value should I write? Well, it doesn't tell me I should change the cell. And if it doesn't tell me I should change it, let's assume it doesn't change. Right? So I was reading a C, and Turing machines don't allow you to say, don't change it. Right? They allow you to write something. So what I'm going to write is the value that was there. And that doesn't, so does it change? Well, I'm writing a 3 on top of a 3. Right? And then, what do I do with my head? I move it right. Right? Everybody got that? So your job is to translate this into this. Can you do it? Yes?
What transition function do we get for the whole state?
We haven't gone to the whole yet. At some point, if I'm in line 89 and life is really good to me, I'm going to stop. Right? So then I'm going to say, if I'm line 89 and life is good to me, then I'm going to go into the halt state.
No, I mean, because you still fill out the last row, right?
Yeah, well, yeah.
Because if you have for the function line 39, you have line of holes, right? Then what state do you go into next?
Halt?
Yeah, so it says line equals 39.
Yeah.
Let's say the whole state is line 80, right?
Yeah.
So then you have to give it the transition.
Yeah, but the code is never going to go from 39 to halt. The code, so when I'm in 39, I go to 40.
Yeah, I understand. But like, what if you're at the halt? Currently, you're at the halt state.
If you're at the halt state, then you stop.
So you don't have to fill at the last row.
Oh, I get your question. No, don't fill out the last row. Sorry, when I said the whole table gets filled out, don't fill out the whole table. Good question. Everybody got that? When you're in the halt state, there's nothing you got to do. You've stopped. Yep.
So I understand that there's like a big jumble of patterns of like all of this stuff in the Turing machine.
Uh-huh.
In order to understand it, you kind of need that intuition of like line 39, blah, blah,
Right.
blah, blah, blah. So
Right.
But when building a Turing machine, you kind of need to know where you want to get to in terms of the code, right? Like you can't just get a Turing machine in a big table and determine, oh, this is for finding maps, or oh, this is for, yeah.
I had a summer job as a co-op student where I wrote a program to compact. You gave it a video, an image in black and white, and you looked at each pixel and you compressed it. And I wrote it in machine code, and it took me 4 months, right? And nobody should write code in machine code, right? That's what you did in the 80s. You don't do it now, right? And so, do I want you to be writing Turing code and understanding Turing code? No. Am I answering your question? It's like, we don't want to be writing this stuff.
Yeah. I just wanted to see like if you could parse meaning out of just the Turing itself, or if you need to have this intuition of like, oh, I'm trying to find a max, so this needs to store the x value here.
Well, I kind of said if the table, you're given a Turing machine and the table looks like it's all spaghetti code and random, you're not going to get meaning out of it, right? And in fact, you probably have heard that the banks have all this code that was written in the 80s in BASIC, compiled, and they've lost the code, right? They're running machine code that was written in BASIC, and they lost it. And so they're busy trying to make changes, and they're trying to decompile their machine code. And my understanding is it's very hard to decompile machine code, right? So if you start with a Turing machine at the bottom, don't expect to rise up and have meaning, right? We're starting at the top and we're coming down, right? Does that make sense? Yeah. What? Moving right. Oh, there's an infinite tape, and there's a head. And every time step, you get to move the head right or left. That's what a Turing machine is, right? A Turing machine. I'm in some state. I read some character from the head. I mean, we're on 9, right? There's the tape, right? I'm in this state, and I read a 0, so I write a 0, and I move my head right. Right? That's what a Turing machine is. How are we doing, guys? You following this? Any questions? Is everybody going to do perfect? Yep. Yep. Oh, the meta algorithm. When I told you, let's go back to it, because we're going to go to the next slide anyway. 90, what was it, 90, we're up here somewhere. I told you that I gave you this and you have to produce this. I also, higher up in the test, told you that X is going to have the range 0 to 5. All right? I mean, the algorithm designer has to design that, right? At compile time, you have to decide what variables do I have. I mean, who decided to have an X and a Y? You decide you have an X and Y. You decide I'm going to have this many lines of code. You decide the range of the variables, right? And so somebody decided that. Everybody good? All right. Right? So this, again, this is now thinking about it as computation. Right? I'm in this state. That's what's written on the blackboard. Right? We have this line of code, and we follow this line of code. What does it say? It says, remember, the first thing you need to memorize right now, do not leave this room until you have this memorized. Right? I have a delta function. It says current state, character I'm reading. Next state, what character I write, what direction I go. Learn that. Because if that's not on your test, you might as well go home. Right? Yeah?
The second character is what we write on the current state and then we move.
This one? This one? This is the character I'm reading. This is the character I'm writing.
On the state we are in.
No, on the location of the tape that the head is.
On the head, yes. On the head.
Right? The head is reading this character. The head is writing this character.
Then we move the head.
And then you move the head. Right?
You don't move the head and then change.
No, because then the next place you read, you'll know what's there already. Right? We have to go to and you move the head so we get some new knowledge and we can read it again. Right? Is that making sense? I mean, we want to write on top of this value. I see this value. I replace the C with that value. Right? So everybody know we're doing that. And now we're working on translating. Right? Now it says, if I'm in this state, and now we're going through levels of abstraction again, right? Here, if I'm in this state, and I'm reading a 1, then what state do I want to be in next? I want to be in that state. Right? Everybody got that? And that's the name of the previous state, right? That's the character we're reading. That's the next name of the next state. That's the character we're changing it to, right? We're changing the Y to a 1. Right? Everybody see that on the blackboard? Right? I keep saying the same things. Right? Everybody getting this? Right? And now more generally, right? More generally, I'm saying I'm in this more general state. Right? Because I want to do this. I don't get too repetitive. I don't want to write it down 25 times. Right? So now I say, right, for all of those values, right? Right? I do what we said we were doing. Right? Everybody getting that? And, right, to keep the number of states finite and the size of the table finite, we must put the values in a certain range. Right? We can't store an arbitrary integer. They have to be within a range. All right? So there, I have my x's ranged and my y ranged. Right? Everybody good? Now, let's look at the difference between x and x prime. Right? They have very different natures. Right? X equals is actually part of the name of the state. Right? If you look at the name of the state, it actually has the characters x equal. But the x prime is a value that's one of these. Right? So these are variables and these are values. Right? It's just x is just part of the name of the state. Right? While x prime is one of those to fill into the name of the state so we can fill in the table fast. Right? Everybody still good? And C is the value we're writing. That's the character we're reading. Oh, here, this is just telling us that we haven't changed the value. Right? I said it, but it hadn't come on a slide yet. Right? And then, now, let's change the code. Right? Now, the code is line 39 is going to take the value that's on the head into y, and simultaneously, it's going to write the value of x. Right? So, we just put an x there. Yeah, so I'm stretching things, right? Now maybe we're expanding the tape so that it can be 0 through 5. Or maybe I know that in line 39, x will only have the value 0 or 1, right? X can have the range of 0 to 4, but I happen to have an invariant that tells me right now X is 0 or 1. Right? I don't know. I'm just giving you some things that you can do. Right? Everybody good? Oh! Secretary. Very good. That absolutely should be a prime. Absolutely be a prime. In fact, I bet you, no, you don't have to write it down, right? No, this is bad, right? This is the type of thing that I look for on a test because it tells me that you're writing the value X as a variable, right? And that's wrong. Everybody see how wrong it is. He saw it was wrong, right? X has no meaning whatsoever. We need to write here 0 or 1 in the table. And what's 0 or 1? Well, the X prime is 0 or 1, right? So, X has nothing to do with the Turing machine other than the name of the states. It's not actually a variable to be written. Right? Everybody getting this? Yeah? No! X prime and Y prime, we have no variables. Right? It's like if you watch The Matrix. There is no spoon. Right? There's no spoon. There's no variables. And you have to remember, you have that one level of abstraction, you need to be writing code as if they're variables. Right? But another level of abstraction, you know there's no spoon. Right? So, right here, we have variables. Right? I have a variable X and a Y, and the code says, read in the value and put it in the Y. Right? So that's the code. Right? But when we translate it into a Turing machine, if I see any evidence of a spoon, then you fail. Right? No spoons. You know what I'm getting here? So here, that looks to me like a spoon. Right? It looks like a variable. It looks like the guy is saying, I'm going to write the value of X into like a subroutine call, right? I'm writing the value of X. And that's bad. We don't have variables. X, the character X, is just the name of a state. It has no meaning in the Turing machine, right? Now, X prime is substitute, right? It's shorthand for one of these. And what can my table do? I can tell you the value that I write here, right? So I don't put here the name of the variable because we have no spoon. We put the value here, right? And what's the value is X prime, right? Right? So here we're saying it again. If X is 3 and Y is 0, the name of the state is 3, 0, right? And what I'm writing is 3, right? So if I'm in the state, this state, then what I write is a 3. That's what my table tells me, right? Column 3, state, this state, write a 3, right? So on if we have something else, I'm in that state, right? Then I write the value of, I write a 4, right? If I'm in a state for which this is the name, forget Turing machines, forget code, forget just Turing machines. I'm in the state who has this name, then I write the value 4, right? Yeah? Yes. Yes.
So y, when we selected, like at the beginning, it was x and y are equals to x prime and y prime. And then when you changed it,
Yeah.
x state x prime, y c.
Right. Well, here I'm just let's move.
Not the previous, the one that like y
Yeah, well, it was coming up again. But where's the typo? Y equals C? Yeah, because the new value of y, I'm reading off the tape, right? So what is it saying? If I'm in a state with this name and I'm reading a C, then the name of the new state should incorporate y to have this value, right? And the value to write is not a variable. The value to write is x prime. Yeah?
What I don't get is, in the line 29, it says, remember x, y equal value at head. So x, on the left, you say x equals to x prime.
Yeah, here, there's a comma here. Remember x. Sorry. Remember x. Y equals the value it had. Move the head right.
So the comma means separation of the string.
I'm just trying to get it all on the string, on the screen.
But usually in the code, when we have a comma, especially like Python, it means that we can assign the value.
I'm not doing Python. I'm doing Jeff's pseudocode. Maybe this should be a semicolon, right? Right? All right, we can try to put semicolons in there, but that's going to be an awfully lot of work for me, replacing commas with semicolons, so I might not actually do it. All right? I didn't even need to say remember x. That was just, an additional thing. You're remembering x. Y is getting the value at the head. I'm moving my head right? And I'm writing the value of x. So that's what we're needing to do. Let's go forward to the right code. Right? Are people kind of following this? Here, I'm just filling in the table. Right? Yeah? No, absolutely not. Right? No, it should not be x. There's no x. X has no meaning whatsoever. It's just characters in the names of my strings. All right? And the other characters in my name of the strings is here. We're going to put the value. Either value might be 0, it might be 1, it might be 2 or 3 or 4. So I'm talking about various states. That this here could be a 0, 1, 2, 3, or 4. And so here, this piece, I take x prime to be one of these, and I plug it into there. Right? In fact, so this, you might want to say, what does this mean? Right? I say, it's a method for filling in the table, right? And now let's write code to fill in the table, all right? What's the code going to do? The code is going to loop over all values x prime in this range, all values of y prime in this range, all values of c in whatever range the characters could be. All right, here I'm applying it could be this range too. The reason I only had 2 columns in my table is because it didn't fit on the screen. All right? I'm writing code to fill in the table. Hold that thought. Right? Everybody see this is a table writing program. Loop over all those values. And then, whenever you see an x prime, substitute in the current value for x prime. Right? It's going to be one of these. Substitute in the value of y prime. It's going to be one of these. Substitute in c, right? And when you substitute in x prime, it's going to get substituted in there. The c is going to get substituted in there. The x prime is going to get substituted in there, right? And that's going to give you how to fill in the table, right? So, for example, here, in this case, x prime is 4, y prime is 0, c happens to also be 0, right? And what we're doing is, right, then the 4 gets put here. And this is the line in the table. So you put that in the table. Yeah? Yeah?
So x at the beginning it was 4, and then it changed to 3. Is that because we moved right? Or?
We did not move. We're filling in the table.
Yeah, but so x at the beginning, like line 39 right there, it says x equals 4, and then line 40 it says x equals 3.
Yeah?
Yeah.
Yeah, so you mean we got another one up here?
We went back to when you use x prime, when you were using x prime before you actually started using numbers. In the beginning, it was x prime, and then after that, it was x prime. But then in the example you just showed us, like if you go back to where we used to be, you had 4 as x prime, and then it changed to 3.
I think everybody's brain is turned off. My brain is turned off. I think we should go home. Think about it. Study the slides. What? Oh, there's a typo. There, we got a typo. Excellent. Woo! I make an awful lot of slides. I think the number of typos is surprisingly small. Just wait. I got to turn these off, and then I got to run because everybody's brains are fried. What am I doing? I'm doing this. Last review class, which was all of yesterday, they asked for more formal proofs of first order logic stuff, and people. So I put an example on the board that they all found too confusing. So then we put a simpler version that they didn't get so panicked about. So as an addict, I've spent all my waking hours when I wasn't briefly in a hot tub and teaching, making more slides. But we're not going to cover them. So if you want to look at those slides, look at the form for the page numbers, and they're on the 1090 slides, which you get from that first link. All right? And I kept trying this way and this way to think about how to prove it, and kind of had this method where we prove it real quick, and then we then get a longer version and telling you how these versions kind of put together in case you care. Now, will you need to know this? There is a question on the test that is worth maybe 7 marks, and it will require you doing a proof like this, and the top level proof is probably good, and my fantasy is that everybody can just do it by playing the game at the top level, right? What are these levels of proofs? The first, you're assuming A to imply B, right? And to prove B, you have to play the first order logic game for B, right? And where's the complexity in is where how do you use the A, right? So in the B, you have to construct something, right? So in the B, you can say, let B be what? Let X be what? Oh, it's the thing that that A is assuming to exist, right? You can put that more into English, right? So I'd be quite happy with the proof that just follows the first order logic of what you're trying to prove. And when you're trying to construct something, well, you just say, hey, we assumed this A, and A allows us to build this, A allows us to compile Turing machines into Java code into Turing machines or vice versa, right? So have it more of a chat. And I think at that level, you don't need to look at any of my new slides, right? Everybody follow that? But you do need to know that the way you prove something at the first level is you play the game, right? You go from left to right, and if it exists, then you prove it's true by saying, hey, exists X, I'm constructing X, right? And if you're proving for all Y, then you say let Y be arbitrary, right? That you need, and these different layers is probably more than you need. Everybody good with that? All right, so what we're going to do now, you guys got me all in a tizzy. I've trained you so well to complain when you're not understanding things, so you're complaining all the time. Right? Yeah, you want to complain?
No, I don't know if you turned on the recording.
I think I did, but let's always check. We did. No, it's all good. It's all good. All right, so what we're going to do, so again, what did I do before our last class here is I went home and I made more slides on Turing machines. And the next example that we haven't worked, I was kind of working it this way before, and I turned it around so that it more closely mirrors what you're going to have to do on a test. All right? So are we understanding it from the bottom up, or are we understanding it from the top down? Right? So I turned it around. All right, so that's, you see here our arrows are going up now. All right? And so on a previous slide, which I skipped past, what am I saying? Is I'm saying the top level of understanding is knowing loop invariants and preconditions and postconditions. And I believe I'm religious about it, right? Anybody who knows me knows that I'm big on them, right? And then in 1030, we just today switched from loop invariants to recursion. So what we've done up so far in 30101 is how do you get code from loop invariants, all right? But that's not this course, right? So in this course, I'm going to give you the loop invariants, and I'm going to give you the code, all right? But you should somewhat understand the loop invariants because it helps, right? The loop invariant tells me what's true when I'm at the top of the loop. And why is that good? Because it tells me what state I am in the top of the loop. And why is that good? It's because you have to build a Turing machine whose state is named after that, right? So if anything, the loop invariant is used to tell me the state I'm in at the top of the loop, right? Which you need to do, because what do you need to do? You need to get from Java code to this meta Turing machine level code, all right? Now, what should you understand? Right? What you need to do is convert from Java to the meta level. But you need to understand that this meta level is not a Turing machine, right? So if you put anything in the meta which convinces me that you don't understand that we're talking Turing machines, then you will be hit very hard, right? So what we're going to do right now is talk about something that you don't need to do on a test, but that you should have an understanding of. And that's how do I convert from a meta algorithm to meaningful names, and then how do I convert from meaningful names to an actual Turing machine, right? In case someday, somebody puts a gun to your head and said, you have to build me an actual Turing machine, you'll know how to do it. Right? Everybody got that? All right. So this is the metacode, right? Metacode has these for all various variables and has this x prime in here, right? And remember, there's no variable in your Turing machine that has x prime in its name, right? So that's what we're doing now, is we're converting from this to an actual Turing machine. All right? And so this is a new slides that I've stuck in here, right? So what we're going to do now is we're going to build a compiler that's going to compile from this to this, all right? And then we're going to write another compiler that's going to convert from this to this, right? So, right? So this is the answer on the test, right? I'm going to ask you, right? So now we're going to compile, right? So here what we're doing. We're given something like this. Suppose, we had this, and we now want to compile it into a Turing machine, right? So what I'm going to give you now, let's remember, this is not a Turing machine. We're not running a Turing machine. We're running a compiler that compiles from meta language to a Turing machine. The output of what we're doing will be a Turing machine. Right? Everybody good with that? So don't think we're running a Turing machine. Right? So what do? Right? So we're going to loop over all possible values of x prime. Right? And we're going to loop over all possible values of y prime. And we're going to, and what are these? These are the possible values that x and y can have, right? If x and y take on values that are integers, then that's what they are. If they take on values which are sheep, animals from a farm, then that's what they will be. But in this case, x and y are taking on integers, so that's what we're looping over, right? Everybody good? This is we're looping over what? Characters that could be on your tape alphabet, right? And in some places in all of this, when I have a chart, it's 0, 1. Why? Because that already fills the screen, right? But in the code, some places, I assume it's 0, 1, 2, 3, 4. Why? So that it lines up with x and y, right? Do we care? No, it's some range, right? All right, so now, given all of those, right, given we know x prime, y prime, and c, right, actually no, forget c. Given I know x prime and y prime, I have to know what state am I in, right? And so I need to know the name of the state. And how do I get the name of the state? Well, a state name is what? It's a string of characters, right? That's just a string of characters. Right? And here I take the integer that's up here and I convert it into a string. Right? And then the plus here is not addition. What's the plus? It's concatenating strings together. Right? You've seen this in Java, haven't you? Right? So I'm getting a string that looks like this, except there's a value plugged in there and a value plugged in there. Right? Everybody getting that? And then I do the same. This is my first name and this is my second name. Right? And then I have to build my table. Right? And so what's my table? It's indexed by states and by characters. Right? If it says I'm in this state, I'm reading this character, then I go to this state, I write that character, and I go right. Right? So I'm filling in this table. So I'm saying, hey, I'm filling one table entry. We're indexing the table by these strings, which is a funny kind of way to index tables by strings. Really, you're going to need to do some sort of hashing or something, right? And we're indexing by the tape character. Right? Everybody follow that? And here, that's an entry into the table. So that we've just converted to a meaningful named Turing machine, right? But we don't like, but a real Turing machine, right? If you're over in, who's teaching it now? Supercash is teaching it now. He might call his states Q1, Q2, Q3, right? So now we're going to convert that. We're going to get rid of that because I didn't know how to have a table indexed by strings, right? So instead, we're going to have some sort of hash thing that's going to take our state names and hash them to unique integers. And ideally, there's no gaps so that we have states 1, 2, 3, 4, right? We're going to hash them down. And then we're going to, here, I guess we take our state name and we hash it to some number, 2 for Q2, right? And what do we do with that? We hash our two states, and now we have a table indexed by integers, and we're filling in our table indexed by integers. Everybody got that? All right, so now, hopefully everybody now knows what is an actual Turing machine, right? Everybody knows we can take the names of the states and rename them. And everybody knows what a metaprogram Turing machine looks like, right? And you sort of have a sense of what I mean by Java code, right? So now what we're going to do is we're going to go through my new example where we're going to start with the loop invariant. We're going to put out code. We're going to turn that code into a meta language, meta Turing machine, and we're going to briefly mention the lower level Turing machines. All right, everybody got that? That's what we're going to do now. And let me be quite frank with you. This is exactly what you're going to do on Monday. All right? It's going to be a slightly different loop invariant, slightly different code. But I'm going to give you the loop invariant. I'm going to give you the code. Right? Oh, actually, I'm being a little mean. I'm also making you argue why the code works, right? You're going to also have to argue for 5 marks or something. You're going to have to say, oh yeah, if the loop invariance here is true and I do these actions, why is the loop invariant going to be true again, right? And for another question, you have to say, right, if the precondition is true and I do these little actions, why is the loop invariant going to be true? Right? And why am I doing that? Because it's my passion and I'm torturing you so that you'll be ready for 3101. All right? All right, so that's what your test is going to... Oh, your test. No, your test is going to have 2 questions. Right? Each of them have 1,000,000 parts. Right? What are the 2 questions? Turing machines, first order logic. All right, that's Monday. All right, so here's just our table. All right, here we're doing. All right, that's what we're doing, right? That would be on the test. All right, so I think this is just chatty, slides you've seen before,